Hello everybody. Today I am starting module number 9 and in that module this is the first lecture. This lecture will be delivered on a very common type of shell, that is a doubly curved shell, symplastic nature. I will use the membrane theory of shell to analyze the particular type of shell, and this type of shell is generally known as shell of surface of revolution. The examples are your domes, maybe your spherical dome, maybe ellipsoid, or maybe your paraboloid of revolution, and the hyperboloid of revolution is also a shell of surface of revolution, but that is having different characters, being enclastic in nature. Okay. The topic of today's lecture is membrane theory of shells of surface of revolution. Now, in the last class I have introduced the membrane theory, and you have seen that membrane theory of shell is nothing but a momentless state of the stresses. So, that is only the membrane stress in the shell structure will be considered, and no bending moment and shearing forces is considered in the formulation of the problem. So, using this theory in the shell structure, we obtain the membrane stresses which are in Cartesian coordinate systems are nx, ny and nxy. Nxy equal to nyx when the curvature is small compared to the thickness. So, the forces, the membrane forces per unit length nx, ny and nxy is our target, and we have to obtain this. But in this kind of shell, that is the surface is formed by rotating a plane curve about an axis of revolution. It will be convenient to use the spherical coordinate system. That means, position of a point can be specified by 3 parameters. One is theta and another is angle phi and radial distance r. So, we will formulate the problem using the spherical coordinate system for shells of surface of revolution. Okay. Now, as I have told, this surface of revolution is formed by rotating a plane curve about an axis lying in the plane of curve. So, say for example, this is your one plane curve, and this plane curve is rotated about the axis of rotation, that is you are seeing a vertical axis, that is the z axis. Then a surface is formed, and this surface is known as shells of surface of revolution. Depending on the nature of the curve, the name of the surface of the revolution is also given. For example, if a part of a circle or a circular arc, which is now in instant case it is a meridian, and if it is rotated around the vertical axis of revolution, then a spherical dome is formed, that is a spherical surface of revolution. But when we rotate a ellipse, a meridian of elliptical curve, then ellipsoid of revolution, like that paraboloid of revolution etc. can be formed. So, any arbitrary curve can be chosen, not only that a part of a circular arc or your parabolic curve or elliptical curve, but any curve you can form and you can revolve it around the axis of rotation to form the surface of revolution. Okay. The curve that is rotated is known as meridian. So, its technical term is meridian, this curve, and the axis of rotation is this, and this type of shell is generally a doubly curved shell, and this is non developable. So, this type of shell is stronger compared to singly curved shell which has developable surface. So, singly curved shell developable surface are examples are in cylindrical shell as well as in conical shell. So, if you give a cut and then apply pressure, then this surface can be flattened completely. So, that is weaker than the doubly curved shell, that is non developable, and here we will consider the non developable shell, that is the surface of revolution. This type of shell is characterized by two principal curvatures, and because these are doubly curved. So, the curvature exists in two orthogonal directions, and therefore, we need to take into account two principal curvature into formulation. Now, here you are seeing that an element of the shell is taken, which is shown by a yellow curve, and then with reference to some axis, say here, which is here horizontal x axis you can call it, and then angle is measured, which is known as the circumferential angle, to locate the position of any point P, because this distance is taken as small distance, and therefore, the position of a point on this arc is defined by this angle theta, that is circumferential angle, and also this meridian. This point is located on the meridian, say this, in this meridian. Therefore, the meridional angle for this point is phi, and radial distance is given by the r from the axis of reference. This again the r is related to the principal curvature of this surface. Now, you can see that when the meridional curve is rotated around the vertical axis, a surface is formed, and the horizontal plane, that is, if you cut a section in the along the horizontal direction, you will get, if you rotate it 360 degree full, then you will get a circle. So, this type of shell you will get the plane that is known as parallel of latitude or parallels of circle, sometimes it called as parallels of circle. Now, doubly curved shells are synclastic, and very common examples are domes, which are seen in case of temple, mosque, and auditorium and other types of large buildings. Large building, I mean that area is large. To provide a column free space, then we construct the thin shell like dome. Ellipsoid, that is in place of this arc of a circle as a meridian, if we take the elliptical curve, then ellipsoid of revolution is formed. Similarly, paraboloid of revolution is also there when a parabolic meridian is rotated. So, doubly curved shell, these are the examples of synclastic shell, and this is an example of spherical dome. This arc is taken as a part of a circle. Okay. Then there is anticlastic shell in the doubly curved group, that is known as hyperboloid of revolution, and that is mainly used in the cooling tower. Examples are this. So, hyperboloid of revolution, that is this type of structure is used in cooling tower. Then this is also a synclastic shell, that is instead of this circular meridian, we have taken a elliptic meridian to form the surface of the shell. Okay. Conical shells are the examples of singly curved shell, and it is developable surface. Okay. But this is also falling under the group of shells of surface of revolution. Conical shell is also formed in the group of shells of surface of revolution. Okay. Now, let us first introduce the coordinate system in which we will work out our problems. So, axis of rotation here is z axis. The position of any point on the surface is denoted by phi theta r. You can here note that phi is the meridional angle by which the position of the point on a particular meridian is located. Then on this meridian, the position of a point circumferentially is also located by an angle theta. So, which is known as circumferential angle, and the radial distance of the point from the center of the horizontal circle or parallels of latitude is r. This r 1 is the major principal radius here, and here you can see the center of curvature, and r 2 is the second principal curvature, but here this r 2 is shown as a intercept or distance between the point under consideration with the point of intersection with the axis of rotation. So, that is here r 2. So, this r, that is the radius of the parallel circle, is related to r 2 by meridian angle phi. So, one can readily see that r is equal to r 2 sin phi. The angle of meridian plane is denoted by theta and measured anticlockwise from a fixed reference plane, and this reference plane is taken here, this plane as say z x plane here, if this is the x axis. Okay. So, now the meridian and parallels of latitudes are actually lines of curvature, and these lines of curvature, this is parallels of latitude one lines of curvature and meridian is one line of curvature. So, these lines of curvature have the principal radius r 1 and r 2. Okay. So, the second principal radius r 2 that I have discussed, I have introduced to you, it is nothing but the point of intersection, distance between the point under consideration and the point of intersection with the vertical axis of rotation. The membrane stress resultant on the element, we take an element, small element, whose length here, this will be your r d theta and width will be r 1 d phi. Okay. That can be readily verified from here, that if this angle is d theta, then the small arc will be r into d theta, if this radial line is r. Similarly, this arc, if this angle is d phi, then this arc length will be this r 1, this distance is r 1. So, r 1 into d phi. Okay. Membrane stress resultants are shown here on this element, that is n phi per unit length, and in the meridional direction, and this is n theta in the circumferential direction. So, n phi is the meridional stress and n theta is the circumferential stress. Okay. N theta phi and m phi theta are the membrane shear forces that are shown on the edge of the element. Okay. On the opposite edges, we consider the increment of this quantity. So, suppose if this is n theta, on the opposite edges the stress will be n theta plus increment. This increment is del n theta by del theta into d theta, taking only first order term of the Taylor series expansion. Similarly, the increment of n phi on the opposite edges will be n phi plus d n phi divided by d phi into d phi, and increment of n phi theta will be n phi theta plus del n phi theta by del phi into d phi. So, you have seen that here on the element, the forces acting along the edges in tangential direction, that is the shear force, and in the normal direction, that is the direct membrane force n theta and n phi, n theta and n phi. So, we have to form the equilibrium conditions of this element to analyze the shell, and then we get a differential equation. Okay. Now, if the load acting on the shell are in general W, and W may have any direction of action, that means line of action. So, line of action of load may be vertical or it may be inclined in any direction, but ultimately for taking the equilibrium condition, we have to resolve the component into three principal directions, that is theta, phi and r. So, three principal coordinate directions will resolve the load and form the equilibrium equations. Okay. So, in this figure it is illustrated that in this element total force is, suppose in this edge total force will be n phi into say this distance is r. So, it will be r d theta. So, that means n, this distance will be n phi r d theta. Similarly, here this force in this edge, this force n theta will be your n theta multiplied by r 1 d phi. So, in this way we can find the total force on the element considering the distribution of the membrane forces on the small element is uniform, because this elemental length is very small. So, therefore, we do not consider any variation of this force along this small elemental length, and therefore, the normal stress or the meridional stress in this direction will be n phi into r d theta. Similarly, the membrane direct force in this edge will be n theta r 1 d phi. So, all the forces can be calculated, and this the membrane shear force, total membrane shear force on this edge will be n phi theta r d theta. Here on the other edge, adjacent edge, the membrane shear force is n theta phi into r 1 d phi. Okay. So, principal curvatures r 1 and r 2 are introduced, and this will be used to form the equation for the stress resultants. Okay. Now, for this element, at any point on the shell surface, we have three principal direction, that is the theta, phi and r. R is the radial direction. So, if say a theta is a unit vector along the circumferential direction, along the theta direction. Circumferential direction we generally call it theta direction. So, a theta is the unit vector along the circumferential direction, and a phi is the unit vector along the meridional direction. In the similar way, the vector a r is the unit vector along the radial direction. So, unit vector I means their directions here are shown in the respective axis, but the magnitude is 1. So, here the shell element is bounded by the angle d phi and d theta. So, that its area is, if this radial distance is r, this area will be r d theta into this arc length will be r 1 d phi. So, area of this element is r d theta r 1 d phi. So, to form the equilibrium equation, we actually collect all the component of the forces in the respective direction and then sum up with proper sign. So, along the direction of the tangent to the meridian curve. What is meridian curve? This is the meridian curve, and this direction, tangent direction, is known as phi direction. So, that is one direction we will take to form the equilibrium equation, that is one equilibrium equation will be formed after summing up all the components along the phi direction. Okay. Phi direction is the meridional direction. Now, along the tangent to the next is along the tangent to the parallel of latitude. So, the latitude you have seen, that is the horizontal circle or this parallel circle that you have seen. So, that in that direction we will again collect all the components and then we will sum up, and that direction is known as theta direction. Similarly, in the radial direction, if this is the center and radial direction is denoted, this positive direction of the axis are denoted with this arrow that is shown here, and in the radial direction again we collect all the components and sum up and equate to 0. So, in this way we will form the equilibrium equations. Okay. So, if the resultant force is R, then we can write this vector equation, say sigma f phi, which denotes the sum of the components of all forces along the meridional direction. So, along the meridional direction, therefore, we assign the unit vector f I, then plus sigma f theta, which denotes the forces, sum of the forces along the circumferential direction, and therefore, we assign a unit vector a theta. Similarly, f r, the summation of this all the forces in the radial direction will collect, and we take it here and then assign a unit vector a r. Now, for equilibrium resultant must vanish. So, therefore, r vector equal to 0. So, that indicates that individually summation of f phi equal to 0, summation of f theta equal to 0, and summation of f r equal to 0. So, the principle of forming the equilibrium equation is that we have shown the differential element and the forces acting on the differential element, and then we will resolve all the forces in the direction of meridian. In the direction of meridian, I mean tangent to the meridian, and then another direction we will take for the sum of all the forces, that is in the direction of tangent to the parallel circle, and then another direction is the along the normal to the parallel circle. So, all these components will be taken and grouped in the respective direction and equated to 0 for forming the equilibrium equation. Okay. So, let us now proceed to find the equilibrium equation one by one. First, we will take the summation of forces along the direction of tangent to the meridional curve. So, along the direction of the tangent to the meridian curve or meridional curve, okay, meridional direction, the membrane force is n phi. So, therefore, the force quantity that I will write here n phi r d theta. R d theta is the length of this arc. Now, here we assign the negative sign, because the positive direction of this unit vector a phi we have assigned in this downward direction. So, that is we taken as the negative sign. Okay. Now, here you can see from the basic figure that radius of curvature of the parallel circle is variable, that is the parallel circle here have radius say r, but at this position the radius is not equal to the radius at this point. So, radius is variable here and radius varies with the angle phi. Okay. So, therefore, we take the variation of radius here, and therefore, the total meridional force in this arc will be n phi plus del n phi by del phi into d phi. This is the force here, this is the force here, and this multiplied by the length of this element. Length of this element is r plus del r by del phi into d phi. Why this length is changed? Because the radius of curvature at this position and at this position it is different, as seen from the this figure. Okay. Radius of the parallel circle here and here will be different. So, therefore, we take this variation of radius with phi. After simplification, that is you multiply each term of this quantity with this quantity, and then neglect and cancel the common terms, and neglect also the square of the small quantities del phi square. Then ultimately you will get this term, because this can be neglected as d phi square is small, and n phi d phi r d theta, that is n phi r d theta. N phi r d theta is your first term, and that is being cancelled with this term n phi r d theta. So, ultimately we are left with this term n phi del r by del phi d phi d theta plus r del n phi by del phi d phi into d theta, and this is taken as 0 because this is a small quantity. So, these two terms n phi into del r by del phi plus r into del n phi by del phi can be written in this form, because r and n phi both are dependent on phi. So, therefore, it can be written in the differential form del by del phi into n phi into r d phi by d theta. So, component of n phi along the tangent to the meridional curve is obtained, that is the phi direction. We obtain the component of n phi in the phi direction. So, we will keep it in store and then we will take it for summation. Okay. The component of n theta along the tangent to the meridian. Okay. Now, n theta force is here in this edge, n theta total n theta will be the n theta into r 1 d phi. In that edge, the n theta will be the circumferential force will be n theta plus del n theta into del theta into d theta into r 1 d phi, because r 1 d phi is the arc length. Okay. So, we have written these two forces on the two opposite edges, and if you see these two forces will have an unbalanced component towards the center, and that unbalanced component can be seen here, because it is the component that we have found on the one edge, total component n theta r 1 d phi. On the other edge, it is n theta plus del n theta by del theta into d theta r 1 d phi. So, resolving this towards the center of the parallel circle, and if this angle is d theta, then this component of this will be n theta r 1 d phi sin d theta by 2. Similarly, component of this force along this radius will be your this n theta r 1 d phi into sin d theta by d 2, if we neglect the contribution of del n theta by del theta into d theta r 1 d phi into sin d phi by 2. So, neglecting the contribution of this quantity, because ultimately this product of two small quantities will be there. So, therefore, we can neglect safely, and ultimately for small angle d theta we can take sin d theta by 2 equal to d theta by 2. So, therefore, we get unbalanced component as n theta r 1 d phi into d theta, and this unbalanced component now can be resolved in the direction of tangent to the meridian as well as along the normal to the tangent. So, this component will be resolved, and unbalanced force we have calculated as n theta r 1 d phi d theta. This unbalanced force has two components along phi direction. Phi direction is the direction along the tangent to the meridian, and radial direction is the direction along the normal to the tangent to the meridian. Okay. So, these two components you are seeing here, that is, if this angle is phi, then after resolving this force along the tangent direction to the meridian, it becomes n theta r 1 d phi d theta cos phi, because if this angle is phi, this angle is 90 minus phi, and this will be again your phi. So, this the component of this force along the tangent direction will be n theta r 1 d phi d theta into cos phi. Similarly, its component along the radial direction will be along the direction of principal radius, that is the normal direction. It will be n theta r 1 d phi d theta sin phi. So, two components we have got, and we have written it, and we will take it when forming the summation of the forces along the respective direction. Okay. So, radial component is this, and this along the phi direction, this is the component n theta r 1 d phi d theta cos phi. In radial direction it will be n theta r 1 d phi d theta sin phi. Okay. Now, we come to the component of n theta phi. N theta phi is in this direction along the tangent to the meridian. So, therefore, the component of n theta phi along the tangent to the meridian is simply the algebraic sum of these forces acting on the two opposite edges. So, you are seeing here n theta phi into r 1 d phi, r 1 d phi is the length of this arc, and similarly in this edge this force is n theta phi plus del n theta phi by d theta into d theta into r 1 d phi. So, after summing up and cancelling some term, we get this, the component of the n theta phi tangent to the meridian, that is the phi direction, is del n theta phi by del theta into r 1 d phi into d theta. Now, we have taken all the components whatever is there are there in the direction of tangent to the meridian. The external load component that have to be now taken. So, component of W, if W is the load acting on this shell surface and its unit is force per unit area, surface area. So, in the phi direction we take the component as W phi, and therefore, total force on this element along the phi direction will be W phi into area of the element. Area of the element is r 1 d phi into r d theta. So, we get all the components along the phi direction. Now, we sum up all the components along the phi direction and we get this equation del by del phi into n phi r del phi del theta, that is one component that we have found out earlier, we have taken here. Similarly, other component we have taken and other component, and then these components are actually one is along the phi direction, another is component of n theta along the phi direction, and then component of n phi theta along the phi direction and component of the external load. Okay. So, after cancelling the common term is d theta d phi. So, we can now write the equation as del by del phi into n phi r minus n theta r 1 cos phi plus r 1 del n phi theta by del theta plus w phi r 1 r, where r is the radius of parallel of circle and r 1 is the first principal radius of curvature. This r can be related to the second principle of curvature by the meridional angle phi. Okay. Now, we get the first equation. So, let us obtain other two equations. Okay. Along the tangent to the parallel of latitude. Okay. Now, the parallel of latitude is the theta direction. Okay. So, this direction, the tangent to this direction is your theta direction, that is we can call it circumferential direction. So, first let us take the component of n phi theta. Okay. So, n phi theta you are seeing that is actually in the direction of theta. So, therefore, summing up the component that is acting on the two opposite edges, we can get the quantity. So, here the first quantity, that is here it is the in this positive direction. So, we take n phi theta del n phi theta by del phi into d phi. So, that is one part. Then length of this arc is r plus dr d phi into d phi d theta, because the radius here is r, but here the radius is not r, radius is changed, radius is variable with phi, that is clear from the diagram earlier shown. So, therefore, radius here will be r plus del r by del phi into d phi. So, arc length of this edge will be r plus del r by del phi into d phi into d theta. Okay. So, this arc length is taken here, and then n phi theta r d theta is the total force along these edges, and it is along the negative direction of the theta, that is along the decreasing direction of theta. Therefore, it is taken as negative. So, after multiplying term by term and cancelling some common term and also ignoring the term with power of small quantities, we ultimately get this as r del n phi theta del phi plus n phi theta del r by del phi into d phi d theta plus del n phi theta by del phi into del r by del phi into d phi square into d theta. So, cancelling this term, that is, this is a very small quantity, we ultimately get this, because this del n phi theta and this r, these two can be combined and we get r into n phi theta and its derivative with respect to phi del phi by del phi, and we get this del phi by del phi r n phi theta into d phi d theta. So, one component is obtained. Similarly, other component of forces in the theta direction to be obtained. Okay. Component of theta phi along the theta direction, n theta phi. So, n theta phi is acting here, and on the opposite edges you are seeing that the increment is given. So, n theta phi plus del n theta phi by del theta into d theta. So, the component of these two forces along the phi direction, along the theta direction, that is in the circumferential direction, is found in the similar way that we have found in the earlier case, the component of n theta along the radial direction and the normal direction. So, in this way we get the component of n theta phi as n theta phi r 1 d phi d theta cos phi, and this is along the increasing direction of theta and hence taken as positive quantity in the summation process to be taken in the later on. So, this total component of n theta phi along the theta direction is now given n theta phi r 1 d phi d theta cos phi. Okay. Component of n theta along theta direction, n theta is here, n theta is in this direction, and on the opposite edge this is n theta plus del n theta by del theta into d theta. So, this component is found just after summation, because these forces are acting along the tangent. So, there is no need to resolve into get the component. So, we take here, because if this direction is positive direction, then this quantity n theta plus del n theta by del theta into d theta is one term, and then minus n theta, because this is in the opposite direction, but with two forces, that is n theta as n theta plus del n theta by del theta into d theta, the arc length is same. So, arc length is r 1 del phi. So, after simplifying we get this force in the component of n theta along the tangent to the parallel circle, that is del n theta by del theta into r 1 d theta into d phi. So, we have got all the components along the theta direction except the component of w. So, component of w along the theta direction, let it be denoted by w theta, and therefore, surface load along theta direction would be w theta into area of the element, which is r 1 d phi into r d theta. So, we get this component, all right. Then adding all the components of the forces along the tangent to the parallel circle, we now get del by del phi r n phi theta into d phi d theta plus del n theta phi by del theta into r 1 d phi d theta plus n phi theta into r 1 d phi d theta cos phi plus w phi r 1 d phi into r d theta, and dividing throughout by d theta d phi, we ultimately arrive at this equation del by del phi r into n phi theta. So, r into n phi theta is a term which is dependent on phi. So, therefore, when we differentiate this quantity, it will be one term will be del r by del phi into n phi theta, and another term will be r into del n phi theta by del phi. And this r 1, which is the principal one of the principal radius of curvature, is appearing here, and del n theta phi by del theta plus n theta phi r 1 cos phi plus w theta r 1 r. So, this is the second equation. This equation equilibrium is in the direction of the tangent to the parallel circle. Okay. Having obtained this second equation, now we proceed to obtain the third equation, which is equation of equilibrium in the radial direction. Radial direction is your normal to the tangent plane, and therefore, after resolving the quantities or forces, we get the components and then we can add it, sum it and equate to 0 to get the equation of equilibrium. Now, you can see if I take the normal direction, that is radial direction, you can tell it normal to the tangent. So, in that case you can see that n phi has no contribution, and this n theta phi n phi theta along the normal, when you resolve it along the normal will have 0 value. So, therefore, these two forces have no contribution towards the equilibrium equation in the normal direction. Contribution of n theta along the normal. So, n theta along the normal direction we have earlier obtained in during forming the equilibrium equations along the phi direction, and one component we have kept in store and now we are utilizing. So, component along the radial direction is n theta r 1 d phi d theta sin phi. This component we have obtained earlier, but as seen here, but we did not use it because we that time we formed the equation in the phi direction. Now, we are forming the equation in the radial direction. So, we take this quantity. Okay. Contribution of n phi along the normal. If you see the n phi, that is the meridional force at the two ends of the curve, say here n phi, total force is n phi r d theta, and here it will be n phi del phi d phi into r d theta. Okay. So, now resolving these two forces n phi r d theta and n phi del phi into del phi, and the radius is here r plus del r by del phi d phi, because r was changing with phi. So, therefore, this variation is taken, and the small angle that is here with respect to your center at the parallel circle is d theta. So, therefore, it is multiplied with d theta. So, arc length is here is r plus del r by del phi into d phi into d theta, but here arc length is r d theta, because r is changing from here to here with respect to phi, and this change is reflected here. Okay. So, after resolving this along the normal direction, then we get this n phi r del phi d theta. Okay. So, this direction is along the direction of the normal. Now, if I resolve it, then we get this n phi r d theta sin d phi by d 2 plus n phi r d theta sin d phi by d 2, and it is nothing but n phi r d theta d phi, because d phi by 2 or d phi is a small quantity. So, sin d phi by 2 is nothing but d phi by 2. So, d phi by 2 is a common factor here, and therefore, it becomes n phi r d theta d phi. So, we got this component along the radial direction. Now, component of W r along the radial direction will be, say the load is W r, then load multiplied by surface area is r 1 d phi into r d theta. So, this component we have got. Now, we form the equation of equilibrium. Equation of equilibrium is formed here, say n theta r 1 d phi d theta sin phi, that is one component. Then another component of n phi towards the normal is n phi r d theta d phi. Then this is the component, radial component of the load. Now, in the definition of load, when we define the load, we have taken the load component W r away from the center. So, therefore, outwards. So, outward direction we take the load as negative. So, therefore, it is written as this minus W r r 1 d phi r d theta. So, total all the quantities are added up, and then we can form the equilibrium equation. Now, here interestingly you can see there is no differential term appearing in the equation of equilibrium. So, no differential term is coming here, because we will ultimately divide the quantities with the area of the element d phi d theta into r 1 r. So, r 1 r d phi d theta is the area of the element, and taking r is equal to r 2 sin phi, that is clear here from the first diagram, that this r is nothing but, if this distance is r 2 and this angle is phi, r is equal to r 2 sin phi. So, that relationship we will use here, r is equal to r 2 sin phi, and then we get this equation n theta r 1 d phi d theta sin phi plus n phi, instead of r we now substitute r 2 sin phi. So, r 2 sin phi d theta d phi minus W r r 1 d phi, and here we write r 2 sin phi, and d theta is already there. Now, it is equal to 0. So, divide throughout by r 1 r 2 d phi d theta sin phi. So, after dividing all the terms by this factor r 1 r 2 d phi d theta sin phi, we ultimately arrive at this equation n phi by r 1 plus n theta by r 2 equal to W r. So, you can see the equilibrium equation is now here in the third case, that is when we summed up all the forces along the radial direction, it is an algebraic equation, not a differential equation. Okay. So, now three equations of equilibrium we can state. One equilibrium equation, that is along the direction of tangent to the meridian, that is the phi direction, is the first equation, that is del by del phi n phi r minus n theta r 1 cos phi plus r 1 del n phi theta by del theta plus W phi r 1 r equal to 0. Second equation is the equation along the theta direction, that is the direction of tangent to the parallel circle. So, this equation is del by del phi into r n phi theta plus r 1 del n theta phi by del theta plus n theta phi r 1 cos phi plus W theta r 1 r equal to 0. and third equation is a algebraic equation n phi by r 1 plus n theta by r 2 equal to w r. So, from these three equation we need to calculate this three quantities actually, that is n phi, n theta and n phi theta. Of course, for the shell whose thickness is small compared to the radius of curvature, then in that case we can take n theta phi equal to n phi theta. Now, having found these three equations of equilibrium, we now come to the case where the axisymmetrical loading condition exists. Now, mainly the shell structures which are used for construction of roof, say dome of a dome in a assembly hall or a religious places or a any large hall, is generally a thin structure and the loading there is only your self load and very nominal quantity of live load, and occasionally wind load occurs, and wind load of course, it becomes a asymmetrical distribution. And in addition to that, there may be some snow load also, but that snow load is also taken as a the symmetrical load distribution. So, therefore, axisymmetrical condition of the surface of revolution is the most common case, and the design we should take into account of the axisymmetrical condition. So, for axisymmetrical condition n phi theta equal to n theta phi is 0. So, therefore, this equation this term will be 0 because n phi theta is 0, and therefore, first equation will be del by del phi into n phi r minus n theta r 1 cos phi plus w phi r 1 r. This term will have no contribution, because for axisymmetrical condition n phi theta is 0. If we look at the second equation, because n phi theta is 0. So, this term is also not necessary, this is also not necessary, and this is also not there. So, that means second equation is actually not necessary in case of axisymmetrical condition. First equation is necessary and the third equation is necessary. From the first equation we can get this n phi, and once the n phi is obtained, we can get the n theta from that equation. Okay. So, we have only two equations of equilibrium in case of axisymmetrical condition, and from this equation, that is this equation number 5 here, we can get n theta equal to w r into r 2 minus r 2 by r 1 into n phi. Then we substitute this equation, that is we obtain n theta equal to w r r 2 minus r 2 by r 1 n phi into this differential equation, and then we get this equation as d d phi, because now we remove the partial derivative sign, because it now becomes an axisymmetrical condition. So, it is not dependent on this two quantities, that phi and theta. So, ultimately it will be only dependent on phi, first equation. So, therefore, we write d by d phi into r n phi into sin phi minus r 1, and this quantity is nothing but n theta. So, n theta we are substituting here as w r into r 2 minus r 2 by r 1 into n phi, and whatever quantity was there earlier we write it sin phi cos phi. Then r 1 w phi sin phi equal to 0. Okay. Now, rearranging some terms and using this expression r is equal to r 2 sin phi, you can see this r is here the radius of the parallels of latitude, and it is related to the second principal curvature r 2 as with the relation r equal to r 2 sin phi. So, substituting this here and rearranging some terms, we get d by d phi r n phi sin phi plus n phi r cos phi equal to r 1 r 2 into w r cos phi minus w phi sin phi into sin phi. and then after arranging this term, these two terms can be written here d by d phi r n phi sin phi. So, that is possible, and after writing this we get a simple expression as this, which can be integrated. Okay. So, after integrating of this expression we get r n phi into sin phi, that is we now getting the value of one membrane stage, that is n phi. So, integrating this expression we get r n phi sin phi, then r 1 r 2 w r cos phi minus w phi sin phi into sin phi d phi plus k. K is a constant of integration. So, from this equation we now obtain n phi equal to 1 by r 2 sin square phi integration r 1 r 2 w r cos phi minus w phi sin phi into sin phi d phi plus k. K is a constant of integration which has to be found from S condition. Now, in case of the surface of revolution having a cut at edges or having the known n phi at one edge or at the other edge, we can find the value of k. So, that value of k when we find, then n phi cannot be satisfied for the condition that exists at the other edge. So, therefore, a corrective term has to be applied. So, this is the drawback of the membrane theory, because the membrane condition, the membrane state of condition may not be satisfied at the edges. So, today what we have done? We have discussed the equations of equilibrium for the shells in the form of surface of revolution, and the equation so derived actually general and can be used for any type of loading. The three equations that I have derived first are general equations of equilibrium, and whether the loading is symmetrical or unsymmetrical, you can use these three equations. But we simplified these three equations in case of axisymmetrical loading, taking the condition of n phi theta equal to n theta phi to be 0, and three equations are reduced to two equations, and out of that we find that one is an algebraic equations, and in one case it is a differential equation, but it is a ordinary differential equation. So, when the differential equation is solved, then we can find this value of n phi, and substituting this value of n phi in the second equation, n phi by r 1 plus n theta by r 2 equal to w r, then we can get the second stress, circumferential stress n theta, because in case of axisymmetrical loading this n theta phi is 0. So, only two forces are of importance, the one is n phi and another is n theta. So, final equations for membrane stress that we have found reveal some drawback of the membrane theory that I have told you earlier, and this drawback you can note that when we want to calculate the constant of integration based on one H condition, and implies that that constant may not be satisfied, or that constant with the equation cannot be satisfied with the condition at the other edge. So, that means a homogeneous correction has to be applied to adopt total solution. So, that drawback has to be removed to find out the or to use the membrane solution near the edges, but away from the edges the membrane solution gives reasonably accurate results. Thank you very much.